Good morning everyone and welcome back to the new video. In this video we will cover chapter number 21, the numeric processor in option pricing. So if we don't have a closed form solution like for American option, so we will use some numerical technique to find the solution of this. In this chapter we will learn about finite differential method, Monte Carlo simulation and some binomial tree and trinomial tree. I hope you like my summary and let's start without any delay. Okay, so when it comes to exotic derivatives, like the derivatives whose payoff is different, payoff is like path dependent, average of path, or barrier type, so you need a different method to price it. And in this Monte Carlo is very helpful. The Monte Carlo simulation, I will tell you, it's a just a random sampling from probability distribution, normal distribution from 0 to 1, and we sample gel Brownian motion from this and we add it to our stochastic differential equation in order to simulate our stock price geometric Brownian motion, and then we find the expectation of it at last and then discount it at present time. And that's how Monte Carlo works. We will cover it in detail. For now we will start with binometry. So we covered some of the binometry in earlier chapter, but in this chapter we will cover in more detail. Binometry is tree method to price an American option because of path dependence. So in this, let's say the stock price start with S, it goes S up, some amount S up and some amount S down, and there is a probability included in it, probability of going up and probability of the flying down. So in general, how we do it? So let's say we are at 30 and it can go 36 and it can go 32. Okay, sorry, it can go 36 then 44, uh, sorry, 24. Okay, and let's say our strike for simplicity is 31. Okay, 31. And so our payoff from this, it is a core option, so its payoff would be st minus k, and its payoff is 31 minus 36, that is 5. And if it is here, the payoff is 0 because it is going down, so there is some probability present in this to find us what is the probability. So our formula is simple, we discount it with probability of into up, so up, payoff of up, payoff of up plus probability 1 minus p of payoff of down, that is sd. And in this way the option price is found. And let me tell you how it is. So there is up moment and up is 36 divided by 3, and let me find to, where is my calculator guy. 36 divided by 30, that is 1.2. So up is 1 by 2 and down is 24 divided by 30. 24 divided by 30, 0.8 I guess. 30, I don't want to be Oh, yes, I don't want to be wrong. Okay, so we have up movement and down movement. So our probability is 1 minus up. Let me check the A, and yeah, our A is E minus RT. So our probability formula is 1 minus D and U minus D, and that is 1 minus 0.8 upon 1.2 minus 1.8, and up value is 0.2 upon 0.4, right? And that is 2 by 4, and that is 50% or 0.5. Okay, the probability is 0.5. So our final discounting would be E minus RT upon 0.5 into S up. S up, our payoff from S up is 5, right? Plus 0, payoff from down is 0, and that, and then probability of going down 1 minus, yeah, and then we discount risk-free rate. Let's take 0.6, risk-free rate and time equal to 1 month, 1 by 12. Okay, or let's, for simplicity, let's take 6 months, 0.5. So our final equation would be 0.6 into 0.5 upon plus 5, right? 5, and okay, I just open Jupyter notebook for calculation. We will just calculate import number np, and always, and then we have np dot exponent, np dot exponent. Our minus is 0.06 into 0.5, and we will multiply it from 2.5, 2.5, and our final option value would be 2.426, and that is 2.426. Simple. Okay, and that's how binomial work. And in each chapter there is some extension of binomial theorem, and we will see it right now. So risk neutral pricing, we are doing pricing of binomial in the risk neutral measure, where interest rate are at risk free rate, and we discount it from discount it with risk free rate. Okay, so let's start our generalized solution. So we have our P, U and D from previous up moment, down moment, S O U, S O D, S O, and P, and 1 minus P. Okay, and the final formula we did here is SE, and where Q is dividend, or a dividend paid yield, or a investment yield from our investment. That R minus Q is our discounting rate then, and delta T for a small period of time equal to probability of S up plus 1 minus P and S down. And we know that from this formula, and then if we cancel out S, the final formula is R minus Q delta T P S U plus S is cut. So probability of up plus 1 minus down, 1 minus P, probability of down. And for variance, we have to find variance also q, right? And the formula of variance is simple: square equal to minus expectation of q square, right? I'm doing right. Okay, square and expectation square, and r is our return, percentage change, and that would be 1 plus r, right? Our total return, $1 of investment, then our return of r would be there. So if we square our equation, because of this, p u square plus 1 minus p d square minus e to r minus q delta t. Okay, and we hence solve it more and put the value and of this, then the final equation we have here is e r minus q delta t and u plus d minus u d minus e square r minus q delta t equal to sigma a t, that is variance. This is variance, and variance formula is given by this if we have to find the variance. And u, from that we can define that u equal to 1d, the down moment is inversely proportional, right? And from that we can find the value with formula, and the variance u equal to sigma t, and d equal to e minus sigma. We all done this equation in our binomial chapter, and it's just a revision. Okay, a, and a is our growth factor. Growth factor. Okay, so let's start a big binomial. Let me show you the picture on it. Would be awesome. It would be easy. Where it is. Look at this tree. Okay, it start from SO up, SO down, then SO square and SO. Why this? It should be SOD, right? But we know that U equal to 1 by D, right? So the value of this, the previous value of this would equal to this. I have to explain it in simple way. We we have a proportionality between u and d, right? And let's see this part only. For from SOU square, up moment is there u, that's why SOU3, but from SOU square down moment is there. Okay, from this proportionality d equal to 1 by u, right? And that equal to SOU square into 1 by u, and that would be SOU, and that would automatically equal to the previous timestamp. And this you can observe in the everything, SO2 square here, and SO4, and there is SO here. So like that. Let me erase it. I hope you understood it. It make our job easier. Okay, and let me tell you the SOUJ and the I minus j. This is the general formula for this SOUJ and the I minus j. Okay, yeah, and for your information, okay, so I is timestamp. You have to understand I is timestamp. The I tends to n till n, okay, and j tends to till I, goes till I, and j is the stock price. So as update for, let's say, and this is delta t at every delta, and del dt equal to t by n. That's the formula. Okay, I hope you get it. SO up moment j, if SO j equal to 1, let's say, then I equal to 0. That means this SO j equal to 2, second order, and d equal to 1. That means this part. Wait, if I equal to 1, if SO equal to 2, okay, if j equal to 2, then I equal to 1, right? Eh? Okay, let's do it again. SOU j, where I, SOU d, and I minus j, or j minus I. Okay, I minus j, and j start from 0 to I, and I start from 1 2 3 4 n, 0 to n, and n is the division, how many path you have to, number of node you want. Okay, and let's say I is 0 and j is 0, then SO. Okay, I is 1, I is 1, and j is 1. I is 1 and j is 1. U, if j is 1, then SOU, and I minus down, it will be 0, then SOU. And if we want this, then we will keep j I is 1, then we will keep I as 1 and j as 2, and that would be j SO2 and I is 1 D1 SO2. What, I am sorry to confuse you guys. I was understanding it wrong. It is a nested for loop that start from 1 equal to 0 till 1 is greater than equal to n, and increment is I plus plus. Okay, and then there is a j that start from 0, and I is j till j is greater than or equal to I, and j plus plus. So in this way, if I equal to 0, and our formula is SO uj and di minus j. Let's say if I equal to 0, then j is also 0, and our value would be SO. One loop is completed. In second loop number 2, I equal to 1, and there is a two option. J can be 0, and j can be 1. If j equal to 0, then SOU 0 and D 1. So SOD, that is this value. Okay, and if SOD is 1, SO up J is 1, then 1 minus 1 equal to 0, then D is 0, and that's a SOT. Let's do it for third timestamp. When in third loop I is equal to 0, wait, we are in our third loop, right? Where I equal to 2, you have to understand how this work, because in coding you have to code it. I equal to 2, then and if j is equal to 0, then SO u square, because of this formula again. And if I go to the j minus SO2, sorry, down moment, SO2. Okay, if I equal to 2, j equal to 1, then our formula would be SO1, and 2 minus 1 is 1, SOD. Again, क्या गलत कर रहा हूँ मैं? SO1, 2 minus 1. तो इसमें क्या गलत है? SUD का है, and हाँ, okay, SUD, and SUD equal to U into 1 by D, and that is S. And if I equal to 2, J is equal to 2, then and the loop will terminate, because our second condition was J should not be greater than to I. J should not be greater than I. Okay. I is okay. And our formula would be SU square D2 minus 2, that would be SU2. And in this way, we construct our tree. Sorry for misunderstanding. Okay. So we understood how the tree work. Okay. And delta t we understood. So how should we price it? Okay. The pricing as per as formula is backward. We start from this, we discount it to this, found this probability, and in this way we work, right? And J is our stock price, this is I is our timestamp. So our formula would be simple. We will take this value for SOU square, pay off from SOU square, payoff, right? For a core option minus k probability plus 1 minus p probability of SOU square minus k, and we discount is E minus RT. Then we get SOU3, then we take this probability, discount it, we get this, then we take this, and we do it for all timestamp. So in finally we get this, and by discounting to SO we found the stock price, we find the option price, sorry. And let's generalize this alphabetically. So its generalization would be Fn function n j equal to max of SOU j t n minus j. You can understand n as a number of timestamp. Minus k equal to 0. Here j 0 1 same thing I told you. It's just a generalization. And for put option it would be k minus this thing. And yeah, so for American we have to make sure if there is early exercisation of option is beneficial, we have to compute that price, compute that value, then the option value. Let me tell you how. So let's say the option price for SO3 is 34, and the discounting, after discounting the payoff in this way, the stock price is at 34, and after, so let's say if here ST minus K is more, let's say 10.14, and our discounting after done by discounting value E minus RT probability of SOU4 plus probability 1 minus P of SOU square is less than 10.14, is less than less than 10.4, then early exercising should be done because the payoff is more. Let's say it 9.9, and here so the option value would be considered as a 10.14 in accounting, and then instead of 9.19, 10.14 will be used for finding the another node option price. And that's why for generalized we compare it like fi say equal to maximum of SOUI uj d I minus d minus k, or discounting binomial formula p of fi plus 1 ji plus 1 plus p 1 minus p fi plus 1 or j. And in this way American option is priced. And if we increase our node to 500 and to 500, the option converges more. The conversion is like this, number of node. Okay, and how to find the delta? How to find Greek? Let's say of f11 F10 and delta, and we have SO up, SO down, and delta is simple. It is like change in option price with respect to stock price, and that would be simple. The option price is this F11 minus F10 upon delta SO stock price minus SOD. Just simple. And if we don't know the, let's say, so to find the delta is easy. To find the gamma, let's say we have more observation. So we have to x, y, z. So we have to find the difference between x, y and y, z, and then we have to find the gamma, right? Change of respect, rate of change of delta with respect to stock price. So here we use h, that the thing is because of SO, S equal to SOU square plus SO half, and S is also equal to SOU square, SOU, SOD square plus SO half. So to compute this, if we equate this, then H equal to 0.5 SOU square minus SOD square, and then it gives us the value of gamma, and gamma equal to F22 minus F21 upon SOU square minus SO minus F21 minus F20 SOU minus SOD square, and divided by H. And theta is easy. Theta equal to F21 minus FOO upon 2 delta T. And for vega, we will add dt term, let's say delta term to it, and dt term would be very small, 0.0001. So if f is x, then our another term is x.0001, and we will construct two binomial model. The f option price from x, and that is f star from 01. We will create two binomial model that would be a little bit same, right? And then we will compute vega. So vega equal to f star minus f, and in same way we will calculate rho. Rho equal to f star minus f with respect to r. Okay, simple. Using binomial for future. Okay, so on stock indices, it is simple. For stock, currency, and foreign currency, stock, dividend, formula is a r minus q, right? Equation 21.7. Okay, little bit wrong, but still, a equal to e r minus q delta t, where q is the return yield from stock, currency, or indexes in simple, and the rest of method is same. Okay, let's make 21.3 binomial model for dividend being stake. So instead of knowing yield, we know when will be when we will have dividend, and we will, what we say, jumped or fluxed our binomial model with respect to that. Let me show you the picture. So let's say we know the dividend will be there of 2% or 3%, 2-3%. So our final value would be 1 minus 2 2%, that will give us so minus 2.3 now. Okay, and the stock price would go down by this amount. If it is 100, and minus 1.3 would be, there is a error. The yield cannot be more than 1%. It is in percent, right? So this will be decimal value. That's why I was like, how can this happen? The SO up moment, SO down moment is more than SO up. It is 130, negative 130. Doesn't make sense, right? So it is in percent. So the whole graph would be brought, whole graph would be, whole SO price would be decreased to lower price, and it adjusted to dividend. And what if we know the dividend yield, exact amount of dividend, then we can discount it, we can minus it from a SO price, right? Like we did in earlier. We know the SO dividend was of 2.3%, then we discount it, uh, SO E minus R minus Q into delta T, and let's say it 50, and after discount it is 49.05, and then we will start our graph from 49.05 with stock price this, and that's the simple logic behind it. And everything is same, right? Like we said, S star equal to S, and S star equal to S minus dividend, discounted dividend, tau minus I delta T. When it is just complicated notation, but the concept is very simple, and we had seen it earlier. And let's see control variate technique. So this is technique used to improve accuracy. So in this we have two similar type of derivative. Let's say European and American. Okay, and we have option on European, option on American. We have to find the American a good approximation of American price. So what we will do, we will build a binomial model for both of them. We will build for European, same process, and for American too. Okay, and we will also find the BS. We have a closed form solution of European, right? We have a closed form solution for European, so we will find BS fine. Then our formula for FA, exact amount of FA, let's give it F star and E star. Okay, so FA equal to F star plus FBGM E BSCM minus E FE. So we will find this and add it with this, and we will get the approximation error. And this is control variate technique. It is very helpful to find the exotic derivative pricing, and we don't know the payoff match the liquid instrument, and we have a solution for a liquid instrument. Then we will match the payoff of both, and we will equate it using control variate technique. It is very important technique, just remember it. And let's see a alternative procedure for creating like binometry, and one procedure is this, where you set u equal to this formula and d equal to this formula, and that probability would always be and probability of will always be 0.5, and it will help us to build a equal binometry. And it's advantageous because sometimes the crosswalks binometry have a negative probability. If there is a large amount of stock and delta t becomes too big, then there will be negative probability, but this will eliminate that. The probability would be never negative. And but the only drawback we have, the to find the Greeks of it would be hard. And let's see trigonometry. Trigonometry is a tree with three parts: first part, middle part, and down part, up, m, d. So probability up movement is given by this formula, down is this, and the probability is this. Probability of down, probability of middle, and probability of, and this is given by finite differential method, and we will see it in later in this chapter. And the final payoff would be simple. We will add all the probability, like e minus rt p u f m and for d. Just let's see time dependent parameter. If in this binomial we assume that r, q, and f is constant, right? But it can be stochastic, like in Heston model, volatility is stochastic, right? So we have to adapt the binomial tree according to that, and it's simple, where ft is a stochastic function and gt is its value at that point, and the final payoff probabilities are given from this formula. Okay, ft is a forward interest rate. It is for interest, let's say interest rate. ft is forward interest rate, and gt is forward value of q or rf. And if we plug the value in it, and we can construct a normal binometry from it. And let's start with another method that is very important, Monte Carlo method. Monte Carlo simulation. You can see from the image that this is the Monte Carlo simulation, and it look very messy, but it is very important tool in pricing. I told you why: to price exotic derivative, to price the payoff, complicated payoff, or part dependent payoff. So here we do simulation. So we from a normal distribution, random normal distribution, we take a value with mean and 0 1, and that is our Brownian term, diffusion term. And with the GBM, geometric Brownian motion, we sample the part, and at the end we find the value. Okay, so and we then discount it. We find the payoff and then discount it, and then we do this for every part, and after the final part, if we do this find the mean, then we will find our value of payoff. So it go like this. Okay, first we sample the random part. Second, we calculate the payoff at the end. Calculate payoff at the end. Third, then we repeat this for every part. If n equal to 1000, we repeat this 1000 time. So we will get 1000 different payoff, right? We get the 1000 different payoff. And fourth, and then we calculate mean, expected payoff, mean, that expected payoff, mean is expected payoff, and then we discount it with risk free rate, and in this way we can find the value of derivative. I have an example. Sorry, I have a project example for you. So this is my project on option pricing of Monte Carlo. Select the stock price, strike price, and maturity and risk rate and volatility and number of part to plot. Then we calculate it. Okay, for core option. Okay, it's running. Then the value is 0.7359, right? This is Black-Scholes formula, the exact solution we have. And there is a discretization scheme. I will not go into it, but Euler and Milstein is a discretization scheme. And for a n equal to 1000, you can see that the option price is almost similar, and the convergence of it is right. See, you can see the Monte Carlo path, and then this is BS formula, and then for two discretization scheme the converges to exact value. And this is a error for Milstein is very less. You can see that it is almost close, and that's the Monte Carlo simulation, and it's easy. First, the simple you have to for let's see the coding Monte Carlo simulation. Okay, we will see Euler discretization. I will print this in this, and then important part of the code. What the result? European core option MC part. And main function. Our main function. Okay, let's start with function number 1. That is our main Monte Carlo simulation. Okay, and there is, see, we can we are fetching the random normal variable from 0 to 1 and saying in the number of part and number of steps. So for every steps there would be a value, and for number of and w is an empty array for Brownian motion, to store the Brownian motion, number of part and number of step. S1 is our stock price, simulated stock price, we will plus 1 till plus, and it start from SO. Time number of time step is time, so n time step is dt. You can dt equal to t upon f, and then we normalized here, normalized with mean. So the thing is minus mean, z minus mean of z upon STP of z. and then the Brownian motion. This is our Brownian motion, dt upon z, right? And then s1, then this is our geometric Brownian motion. This is our geometric Brownian motion. You can see that so s minus s plus 1, that is s plus 1 equal to s minus plus r s dt plus sigma w t plus 1 minus w t, and discretization form of, and then we store every value of s in time and s1, and we have another function that calculate the payoff, discounted payoff, right? See the mean of, you can see we discount it with the mean of, and then we find the mean of s minus k, and that is our final formula of return, okay, for European price. And here you can see we find the Bragg scores formula priced, and then for every part we calculate Euro and and then we price it, and in this way we price the derivative using Monte Carlo simulation. And in book I will go fast from here. In book you can see that this is the Monte Carlo, and this formula we used. You can see I used this formula, and this is our geometric Brownian motion. Yes, and the rock form of GBM. This is GPM. And anything to say that I explain it in simple way. There is just theory around it, and there is another term like correlated Brownian motion. I saw the correlated Brown. I explained the correlated Brownian motion very well in our Brownian motion chapter, so I will not do it here. But you can see that where there is a one univariate normal distribution, and there is another new normal distribution, and this correlation between is set by a term, correlation term, and this can be find from a Cholensky decomposition. And to explain Cholensky decomposition, in book it is not explained very well. So there is a matrix factorization technique used to transform correlated system in quantitative correlated asset. That's simple. But I want to say Cholensky matrix. See, this is our Brownian motion, and the Cholensky the correlation for two people are two asset are this, and this is Raspens transformation and Laplace transformation, and after Laplace transformation we get this value, and yeah, it's a little bit complicated, but it helps us to decompose the value into a smaller triangular formula. So if you plot this, it would be like alpha 1 0 0, alpha 2 will consist of this 0, and alpha 3 will be epsilon 3 will be this, and this is the lower triangle, and we have our correlation matrix. Then we will convert it into a Laplace transformation 0 0 p p 1 1, and then we multiply its dot product, and we have a matrix for correlation for every variable, and it helps us to find correlated paths. And let me show you the project on it. Mm, it is taking time. For now, let's go to next step, the number of trial. If our n trial is large, we have a n value is large, then the convergence is better because raw of large number. The number of sampling is will be more, and then our convergence would be more because of it. And the error is found with this formula, where this is mean and this is standard deviation, right? Omega is mean and this is standard deviation. Omega is standard deviation. Omega is standard deviation, and okay, omega is standard deviation, and m is number of trial. Here you can think of n. So this is standard error, called as a standard error, and with the 95 confidence interval. The app is working now. Correlated Brownian motion. See, if there is a zero correlation, they are random. If there is a positive correlation, you can see they are following the same path. If there is a negative, it will be negative. Opposite to, if there is a down, then there is up. There is a down, there is up. Up, down. In this way, the Brownian motion will act. And the Cholensky decomposition help us to multiply the matrix. Okay. And number of trial. Okay, we found that. Let me go with the book. Now it is easy. With 95 confidence interval, this formula is there. And sampling through tree. So this sampling through tree method, we can use Monte Carlo simulation with binomial tree. How? Let's say how we can fetch a sample value from 0 to 1, right? If the value is, let's say, at time so, okay, if value is 0. More than 0.4, we will say there is a up movement. If ref value is less than 0.4, then there is a down movement. Again, we will sample the random variable. It is 0.6, then it is up movement, up and down, up and down. And in this way, we can also do Monte Carlo simulation with binomial and payoff, and then we will find the payoff of at the end and discount it to today's value. And finding Greek value in Monte Carlo simulation is easy. So we have a simulated part of each, right? Then we will, if SO is 0, then we will add 0.1 or very small value to it and do a Monte Carlo simulation again. And then the derivative price f star is s star derivative price minus f hat upon ex, and in this way we can find the delta, and it is easy. We just add a different path and the Monte Carlo, as we say, it is used in very much in finance, in risk management, scenario analysis, and everything, and various reduction process. Okay, variance reduction project process. This is now let me go through this only. It would be with book. Okay, we are on variance reduction process. So we examine the number of variance reduction process that lead to dynamic saving computation time. So we have to save the computation time of Monte Carlo simulation or make the convergence faster. So first method is antithetical variable, antithetic variable technique, and it is simple technique. If we are deriving epsilon from random normal, from normal distribution, then we will also simulate a part with negative epsilon. We will simulate the path of negative epsilon. If the value is 0.1, then we will also calculate the payoff from value minus 0.1, and the f1 is from positive, f2 is from negative, and then we take the average. Just in this way the convergence is faster and the error is low, and this is standard error is rho 10 2m. Control variable technique, we discussed it earlier. Let's say there is an exotic derivative, right? Exotic derivative, and there is a European core, and the payoff of exotic derivative is similar than payoff of European core. Let's say it's type of. So we will do Monte Carlo simulation of both, and we get the value of FD star and FC star. Okay, we got the value. We also have the analytical solution, that is DS solution, for both of for European core option. So we will also have a EBSM. So to find the derivative, actual derivative price of exotic derivative, that would be equal to EF equal to FD, and we will minus the find the error in both EBSM minus f from Monte Carlo simulation, and in this way it helps us to find the exotic derivative, and it is explained here. Fa is a derivative, we don't have analytical solution, but Fb we have an analytical solution. So we do Monte Carlo simulation of both, and we it should be Fb minus F star b. It will be easy. Then we will find the difference between it and add up with our answer, and in this way we get the final answer that is more accurate. And importance sampling. So importance sampling is a way let's say we are pricing deep out of money option, and for that if we are following normal, the maximum part value would be 0 because it is out of the money. So we for a strike price, let's say 50, we will not we are sampling out of money derivative, let's say, and it is a put option. So we will sample, uh, give like a condition that sample the strike price from 40 to 100 only. So we will get sorry, we will not consider dip out of money. So for till 50 we will sample the value from 0 to 50 in such way that the most probability of exercising would be more, and that is important sampling here, you can say, because of zero payoff, and this is the probability distribution of stock condition. So stratified sampling is a type of sampling. Let's say we are sampling, this is our normal distribution, and then we divide our normal we derive our sample from it, then we divide the sample into normal distribution, and we derive the sample from an area, mean of area or a median of area from it, from every area. So in this way we can say that all the sampling are in uniform form, and we have every probability, that is stratified sampling. And it's in case of standard normal distribution where n interval, we can calculate the representative value of ith interval is ni I minus 0.5 upon n. And moment matching, this is very important method, and we really use the moment matching. So there is a four moment, right? First is mean, second is standard deviation, third is, I guess, mean, standard deviation, variance, fourth is kurtosis. These are moment of statistic or moment of distribution. So mean is mean of a distribution, standard deviation is how how data is different. uh, how data is va- variate from mean, and the variance is the distribution, the broadness of distribution. Kurtosis is the rent of tail. My full moment is like first is mean, I know, second is variance, third is skewness. Yeah, I knew that. First is mean, variance, skewness, how skewed data is, ref skew, mean skew, and then kurtosis. Okay, so we have to match the data from a real market, right? Improbability or anything. So to match the data, we have to match the moment of our world and the normal distribution world. And in this way, this formula help. It is very simple formula, the moment matching, where I and the value from value from sorry value from distribution. Okay, the value from distribution minus mean of it and standard deviation of it, and in some kind of way we normalize it. This is also called as a normalization, right? And we match our moment here, and we done our moment matching here, where it is, see, we minus mean of it and standard deviation of it, and we normalized it. In this way the data is very distributed, and all the data come into one distribution. Moment matching. Where is the book? Crucial random sequence. I really don't understood this. Let me chat GPT it. I didn't got this. So, this way we get the every distribution, the spread point, every spread point, and from every distribution, and that's it. It's little bit complicated for maths. The maths is complicated, and the resources, the book, in book they didn't explain very well and it was confusing. For now, you can understand that evenly distributed data. And now finite difference method, one of the important method in derivative pricing and in differentiation. And I will go fast from it because there is nothing to explain it. It's just a formula. Finite differentiation method. Where is my board? So find the differential equation. We have HD, right? We have to find the solution of HD to find the payoff. And in this way, we can find the solution because it is continuous. We have to discretize it. So the one approach, this is our Black-Scholes differential equation for dividend, right? And we divide delta t equal to t by n, and then we have a array board of t delta t, and then we have x max till s max, the maximum value of stock price, and we have our board, our grid. Okay. What the fuck? This is the grid we are talking about, right? Okay, and the finite differential method gives give that the next value where I is a time step and j is the stock price. You can understand the stock price. Our grid is from m plus 1 and n plus n, and we define as ig as a grid point. Okay, and the finite differential value is just the n plus 1 n plus 1 minus n on 1 delta s. This is the finite method. And or you can do as n minus 1 n minus 1. This is future price, yeah, the next future price of a grid minus the today's future price divided by delta s, and all a backward method, today's divided by yesterday's. And in this way the differentiation, that is implicit finite method, works. And from both we got this, and it's just a formula. I don't know what to explain here. With respect to t, with respect to t, and second order derivative, that's interesting. So it is backward, forward, this is forward minus backward, and delta s, or this formula, forward minus backward upon delta s, and we get the second order derivative. And then there is a boundary condition. We have the stock price here is 0 and maximum is also 0, I guess. Explanation of this is not good. This is our grid, right? The maximum value of derivative here can be k, because for a put option it will be k, here it is 0, and we got, and then we find the every value at this point. Okay, let me explain you. So we have all the value of second order of derivative term with respect to time, with respect to s. We have this formula, right? Then we put this formula in our ds equation form, and then it gives us the value, the coefficient value of each, and this is implicit method, and this is a boundary condition. At fn, if n is maximum, s is 0, then our value would be k, and these three are the boundary condition. You can read that. So fn minus 1, it would be k, fn minus m would be 0, this would be k, this would be 0, that means, and then we solve it, just solve it, and there is a explicit method. This was implicit, and implicit was more computationally dense. Then we, there is explicit method where if there is a matrix, how can I explain? You have to imagine a matrix. Implicit method. So so f5 plus 1, you just remember the formula, I don't know what to explain that. So f5 plus 1 minus back, it is backward forward method, plus 1 minus plus 1 minus 1. Okay, and for second order derivative, this is the formula, plus 1 minus 1 and 2 forward, 2 now, value of today, and after solving this, the value of coefficient is given by this method, that is explicit finite method, and this shows the relationship. See, fi plus 1 is the value we have to find, nj, and fij plus 1, fij, and fij minus 1, we use this value. And for explicit, fi plus 1, j plus 1, fi plus 1, j, fi plus 1, and j minus 1, and change in variable. Now we are applying finite differential to Brownian motion, and how it changes, we are looking at it, and then the value of this is given, and this is the equation, and alpha, beta, gamma of our equation is given, then we solve it, and the trigonometry are based on this. The probability of stock going up is this, probability of stock same is remaining same would be this, and the probability of stock going down would be this, and this is the diagram in the book. What's that? The problem with explicit, okay, here the problem with explicit is given. So you can see that when s is greater than, when the option left hand become negative, and the probability cannot be negative, that's why we can't use explicit so much. And there is another finite method that is called as a hopscotch method, where we use explicit or implicit method both, and the grid, you can see that there is a boundary condition. Implicit method is used for this explicit, implicit, explicit, and this is the form explanation formula. And it is help us to type of derivative for American. And yeah, but it is very computationally heavy, so Monte Carlo simulation is preferred more. And now apart from this, there is more numerical method like Fourier transformation, cos method, cos Fourier transformation, cos method, cosine method, and absolute ES method, exact solution, and characteristics function. We use characteristics function and many more. It was the basic. We will cover it in the next chapter. It was very long video for me to record. Thank you for watching, and I am very sorry about my last explanation. It was not so good, but I don't know what to explain. It's just a formula. Thank you for watching. Bye bye.